All right, welcome. These are the notes for section 1.4 of pre-calc, day 1. We are looking at our objectives today of adding, subtracting, multiplying, and dividing functions. And we will start looking at compositions of functions, and then tomorrow we'll start working on decomposition. All right, so knowing how a function is put together is an important first step when applying the tools of calculus. So how can we put functions together? The first option is just to do our basic operations, adding, subtracting, multiplying, and dividing. Our formal definition says let f and g be two functions with intersecting domains. Then for all values of x in the intersection, the algebraic combinations of f and g are defined by the following rules. Now, I want to be very clear, when it looks like this, it is really saying this. All right? We're taking function f of x and adding function g of x. Many students get confused. It does not mean that we are multiplying by x. Okay? It's just saying we're going to add f and g, and both are using x as the variable. All right, so we have adding, subtracting, multiplying, and dividing. Notice with division, we do have to be careful that our denominator is not 0. In terms of identifying the domains, it says in each case the domain of the new function consists of all numbers that belong to both the domain of f and the domain of g. In other words, it has to be common to both functions. As noted, the zeros of the denominator are excluded from the domain of the quotient. We just talked about that here. So looking at our first example, our function f is just an x squared. G of x is the square root of the quantity x plus 1. So the first thing I want you to do is think about the domains for each individual function before we start adding, subtracting, etc. So for f, domain of function f, we have a function of x squared. There's no values that we can't square, so our domain would be all reals, from negative infinity to infinity. For g of x, though, because it's in a square root symbol, we have to worry about that x plus 1 cannot be negative. It can be 0, but it can't be negative. So that means that x has to be greater than or equal to negative 1. So our domain would be from negative 1 on up to infinity. All right, now we're going to look at adding, subtracting, multiplying, and dividing the two functions. We want to simplify as much as we can, but there will be some that we can't do a whole lot with. So f plus g says take our function f and add our function g to it. Okay? F minus g, we're just subtracting that g function. Okay? For f times g, we are taking x squared times the square root of x plus 1. And then for f divided by g, we are taking x squared. We're dividing by the function g, which is the square root of x plus 1. And the last one they said is to take g times g, which really is the same thing as saying g squared, right? We're timesing it by itself, which would be our square root of x plus 1, but now we're going to square it, which is going to cancel that out, and we're going to end up with just a plain x plus 1. Now, I do need to have you go back and look at the domains, because it asked us to give the domain for each of these combined functions. It has to be in the overlapping section. So let's go back to f plus g. For the x squared, we said that the domain can be anything. But this piece here, the g part of that, limits it. So we do have to go with the part where they overlap, which would be the smaller domain of negative 1 to infinity. Okay? Same reasoning applies to our subtraction version. Our domain would still be negative 1 to infinity. All right, the overlapping part. And the same with f times g. But with the division one, we have an extra issue. Because g of x is now in the denominator, we can no longer have that be 0. So when we first looked at the domain of g up here, we said that the domain had to be greater than or equal, for x plus 1 had to be greater than or equal to 0. So x had to be greater than or equal to negative 1. But if we put a negative 1 in here, it's going to create a 0 in the denominator. So my domain for the division one is a little altered. We have to actually be greater than negative 1 for that to work. For the last one where we were taking g times itself, notice that the square canceled the square root. So when you look at your final answer here of just a plain x plus 1, it doesn't appear like there should be any domain restrictions. However, we do have that domain restriction from back here. All right, we can't use function g when x is less than -1. So we do have to go back and say that our domain is going to be from -1 on up. All right, let's look at another example. This time we have the function f of x being 1 divided by x minus 3, and g of x is the square root of x. So go ahead and pause the video. I want you just to identify the domains of f and g before we start doing anything with the two functions. All right, let's look at what you did. For function f, the only value that we can't use for x would be a 3, because if we put 3 in the denominator, it would turn into 0. So my domain for f is everything from -infinity up to almost 3, jumping over and then going on past +3. Okay? For g of x, we have the square root of x. We cannot square root negatives, so we have to be 0 or higher. Okay? Now again, we are going to add, subtract, multiply, and divide them. The first one says to take f plus g. So we are going to take 1 over x minus 3 and add to it a square root of x. Okay? Domain restrictions, remember, have to be domains that overlap. So because we have this square root piece, right, where our domain had to be 0 or higher, we cannot use anything negative. But we also have this issue where we had to eliminate the 3. So my domain for this first one is going to be starting at 0, but jumping over the 3. Okay? For f minus g, we are going to take our function f, 1 over x minus 3. This time we're subtracting the square root of x. But in terms of our domain, it would be the same as part A. All right? So the domain is still everything from 0 on up except for 3. All right, for f times g, we are saying we have 1 over x minus 3. We're timesing it to the square root of x. Now we could simplify that a little bit and just say that that is the square root of x divided by x minus 3. We still have our domain restriction where x has to be greater than 0, greater than or equal to 0, but it can't be 3. So same domain that we've had for the previous two parts. Okay? But now we get into division, and remember with division we are creating a denominator that we have to make sure is not 0. So for this function, we are taking f and we are dividing by g. Okay, looks a little messy. There are two denominators now that we have to worry about. The first one is right here, so we know that x cannot be 3. And the second one is down here. And we used to say that with the square root of x, it could be 0 or anything higher. But now because we've put that square root in the denominator, it can't be 0 anymore. So now we're looking strictly at above 0 for that. So when we combine those two, we are saying that x has to be above 0, but jumping over 3. Okay, so very similar to the previous domains. However, this is a rounded bracket here because we can't have 0 in the denominator. All right, for g divided by f, now we are taking the square root of x and dividing by 1 over x minus 3. Okay? Looking at our denominators, we can't have a 3. The square root piece is in the numerator, so we are looking at everything from 0 on up. So if we combine those two, we are saying from 0, jumping over 3, and then going to infinity. Okay? Now, for parts D and E, where we had the division, we could do some simplifying. For part D, we are taking 1 divided by x minus 3, and then we're dividing by the square root of x. So we could write that as 1 over the quantity x minus 3 times the square root of x. Simplify it that way. For part E, simplifying, we are dividing here by 1 over x minus 3. Dividing by a fraction is the same as multiplying by the reciprocal. So we can simplify this expression to be the square root of x times the reciprocal of 1 over x minus 3, which is just x minus 3. The one thing you have to watch out for is that when we've simplified this one, like we have right here, we've eliminated the denominator, but the denominator still exists from back here. So make sure that you do your domain restrictions before you've simplified the fraction. Now, as you continue on in math, you will remember that the square root of x is the same as x to the 1/2. So if you really wanted to clean this up a little bit more, we would take x to the 1/2 times x to the first, which would get us x to the 3/2, and then x to the 1/2 times -3, which would be -3x to the 1/2. That's another way we could have written that. All right. So we've looked at adding, subtracting, multiplying, and dividing functions. The last topic for today is the idea of a composition of functions. This is where we put a function into another function. So it says let f and g be two functions such that the domain of f intersects the range of g. The composition f of g, written like this, okay, that's read f of g. We have two ways of showing that. Some books will write it like that, f of g. Some books will put it like this. We're basically saying that we are taking g of x and we are dumping it into function f. Okay? So we put x into g, and now we're putting g of x into f. The domain of that composition consists of all x values in the domain of g that map to g of x values in the domain of f. And our picture below here hopefully will make that a little clearer. It says the composition g of f, notice the order here. Now g is first, g of f is defined similarly. In most cases, g of f and f of g are different functions. All right, so function composition is not commutative. The order is extremely important. So based on our picture here, we are starting with some x values, and x has to be in the domain of g if we're going to plug it in. So we're going to put x into g, and we end up with g of x. Then that has to be in the domain of f because we're going to take that g of x now and plug it into function f. Okay, so that's what a composition does. So our second example here, it says let f of x equal e to the x and g of x equal the square root of x. We want to find f of g and g of f and verify numerically that those two compositions are not the same. So let's first start out looking at domains. So our domain for function f was e to the x. Are there any values that we can't plug in as powers of e? So e we can take to a negative power, we could take to the 0 power, we could take to positive powers. So for the domain of f, we have everything, all reals. For g of x, though, we've got that square root again. So the domain of g has to be 0 or higher. We cannot square root negatives. All right, now let's look at the two compositions. The first one said to take f of g. I typically write it in the other format like this. So I know that I'm going to take my g of x function here and I'm going to plug it in to function f. So I'm going to start with function f, which says e to some power, and I'm going to replace that x with my g of x here, which was the square root of x. Okay? So the composition f of g gives me e to the square root of x. Going in the reverse direction, we have g of f. This means I'm going to take my g function and I'm going to dump my f function into it. So starting with the g function, which was the square root of something, now I'm going to dump in f of x, which was e to the x. I'm going to plug that in. Okay, so simplifying, we've got the square root of e to the x. Now, looking at domains. The domain for the first composition, we had e to the square root of x. We said x can't be negative, so my domain here, since I'm square rooting x, my domain has to be from 0 to infinity. For the second one, I am square rooting the quantity e to the x, which means that e to the x cannot be negative. Okay? But if you think about what the graph looks like, if we graphed e to the x, it's a basic exponential function. Remember, e is that number 2.718. We're raising it to an x power, so it's exponential growth. So our graph would look like this, which means e to the x is always going to be positive, right? It's going to be above that x-axis. So our domain here would be everything. All right. Then it said as the second part, verify numerically that the functions f of g and g of f are not the same. So let's just plug in a number. Let's say we pick 1. And let's plug in to both compositions. So we're going to do f of g of 1. And then we'll do g of f of 1. And we'll just see if we get the same answer. So the first one said, take f of g of 1. We've got this expression for f of g, and we're plugging in a 1 for x. Well, the square root of 1 is just 1. E to the first power is just e. If we do the same thing with our g of x function, which was the square root of e to the x, and now we're putting a 1 in for x, we have the square root of e to the first, or the square root of e. And notice that these two are not the same. Okay, so we verified numerically that the two compositions are not the same thing. So you do have to be very careful of the order that you're doing the compositions in. All right, example 3. It says finding the domain of a composition. Our first function, f, is x squared minus 1. So what would the domain of f be? What are the values that we can plug in and square? It could be anything. So negative infinity to infinity. Our g of x function is, again, the square root of x. We've talked about that. It can't be negative. So we are looking at everything from 0 on up. Okay? And notice that we are doing both compositions, g of f and f of g. So remember, this one says start with your g function and put f into it. Okay? So I'm going to start with my g function, which is the square root of something, and I'm going to dump f of x into that. Okay? I want to put f of x inside of g. So f of x was x squared minus 1. We're putting that inside the square root symbol. All right, looking at the domain of this one. Now we have the quantity x squared minus 1, and it can't be negative, okay, because we're trying to square root it. So that means that x squared has to be greater than or equal to 1. And if we think about the graph of that, all right, x squared minus 1, if we graphed y equals x squared minus 1, we are going to have a parabola that's been shifted down 1. and we are looking for where we are above 0, right? We want it to be greater than or equal to 0. So that means we're looking at this section and this section. So my domain here is going to be split into two parts. The first part is everything to the left of this. So my domain would be from negative infinity to that value, which if you think about it, if we put a 1 in for x here, we get 0. So this would be 1. If we put a negative 1 in for x, this point here is negative 1. So we're up to negative 1, and then we have to jump over the part where this red graph is below the x-axis, and then carry on beyond it. So past the 1. All right, let's look at the second composition. This time we're doing f of g. So that means I'm taking my function f and I'm dumping my function g inside it. So I'm going to start with f, which is something squared minus 1, and then I'm going to dump g into it, which was the square root of x. Now simplifying this, when we square something that was square rooted, it cancels out. We just get x minus 1. But we do have, sorry for the bells, but we do have to look at the domains from the original functions. Okay? When we do a composition, we need to look at restrictions on the inside function, what we're dumping in, and then restrictions on our final answer. Well, our final answer doesn't have any restrictions here, but g of x did. So my domain here is going to have to be based on my g of x function, which says I have to be everything from 0 on up. Okay? So once again, when we look for those final domains of our composition, we are looking at domain restrictions of g of x, the inside function that we're dumping in, and then any restrictions on our final simplified answer. All right. Down below here it says graph each of those compositions and check the domains. So if you graph on your calculator the composition f of g, all right, you should see everything from our line, right? This would be y equals x minus 1, which means we're going to start here at negative 1. We do a positive 1 slope, but we only want it from 0 on to the right. So we would have this portion of our graph. Okay? For the first function, where we were doing g of f, when we graph that, we are going to see two parts. We're going to see this part and this part. And again, if you compare the domains, we said we had to be to the left of negative 1 or to the right of positive 1. Okay? So you can use your calculator to help verify. Just be careful because there are some issues with calculator error that we talked about previously. All right, we're going to try a couple more compositions focusing on how we find that domain. So back to those first couple functions where f was 1 over x minus 3 and g of x was the square root of x. We already determined that the domain of f is everything but 3. So from negative infinity, jumping over 3, and continuing to positive infinity. The domain for g, we said because it was a square root, it can't be negative. So 0 on up. All right, let's look at compositions now. The first one says take f of g. So we're taking f and we're going to dump g inside. So my function f is 1 over something minus 3, and I'm going to dump g into it. So I'm going to have a square root of x being dumped in there. Okay, now there's really nothing we can do to simplify that other than take out those parentheses. Okay, but when we look at our restrictions, we focus on g of x, the inside function. So we know that we have to be 0 or higher. And then we also have to look at what would make the denominator 0 now, because in my final composition, I have a denominator that looks like this. So we want to make sure the square root of x minus the 3 can't be 0. So I'm going to add the 3 over, and then I'm going to square both sides. So we're saying x can't be a 9. And if you think about it, if you put a 9 in here, you can see that that would give you a denominator of 0. So for my domain, we said focus on g, and then anything new that pops up in my final answer. So we have to eliminate 9 and be above or 0 or higher. So my domain here is going to be starting at 0, but jumping over 9. Okay. For our second example, we are looking at the reverse, g of f. So I'm going to start with g and dump f into it. So I'm starting with the square root of something, and I'm going to dump f into it, which is 1 over x minus 3. Now, we can square root the 1 on top. It's just a 1. But we do still have the square root of x minus 3 in the denominator. So looking at domain restrictions, we said, on the inside one, which we said we can't use a 3. All right. And then we also have to look at our new answer, which has a square root in the denominator. So we can't be 0 and we can't be negative. So we've eliminated 3 because that would make it 0. But we also need to make sure that it's going to be a positive value. So x minus 3 can't be negative. So we have x having to be greater than or equal to 3. But because 3 would make this 0, we have to restrict this to x being strictly above 3. So my domain here would be everything above 3. All right. Our last two compositions, we are doing a composition of itself. So we're plugging a function into itself. So for this one, we're taking f of x. All right. Our f function was the 1 over x minus 3. So we are going to take 1 over something minus 3, right? 1 over x minus 3. And we are going to dump the same function into this empty parenthesis. Okay? So it gets a little bit messy. We want to clean it up the best we can. So looking at this, we've got 1 divided by 1 over x minus 3 minus a 3. And when we talked about this last month, we said we can get rid of those fractions by timesing by the LCD, which in this case would be the x minus 3. So let's times the top by x minus 3 and the bottom by x minus 3. Okay? So we end up with x minus 3 on top. Here we're taking this times x minus 3, which is going to cancel out and just leave us a 1. And then we're taking negative 3 times x minus 3, which gets us negative 3x plus 9. So it simplifies down to x minus 3 over negative 3x plus 10. All right. So looking at domain restrictions, we said we have to focus on restrictions of our inside function, which was to eliminate the number 3. And then we look at domain restrictions on our final answer. So let's look at what makes this piece here equal to 0. So negative 3x plus 10, we don't want it to be 0, which means negative 3x can't be negative 10, which means x cannot equal 10/3. So in addition to eliminating the 3 from this inside function here, we also have to eliminate the number 10/3. Okay, so my domain, we're going to start at negative infinity, we're going to jump over 3, and then we're going to go from 3 and jump over 10/3, and then we can continue on past 10/3. All right, our last one for today. We're taking g of g. All right, g of x was our square root function, so that tells me I'm going to dump a square root into a square root. Okay, so we have the square root of something for our outside function, and inside we are dumping the square root of x. If we think of this in terms of rational exponents instead of radical symbols, so instead of the square root within a square root, let's think of that as x to the 1/2 being raised to a 1/2. So we have the square root of x being square rooted. Powers to powers we multiply, which gives us x to the 1/4, or the 4th root of x would be another way we could simplify that. So domain restrictions, based on my inside function, which was the square root of x, we said x has to be 0 or higher, something non-negative, and that same thing would apply to our final answer here of the 4th root of x. So my domain would be everything from 0 to infinity. All right, so tomorrow we will start looking at some decompositions, in other words, taking something that was already composed and undoing it. All right, so for your homework today, you are going to start on page 116. You're doing 1 to 13 odd and 15 to 20. You are allowed to work together after everyone has finished watching these notes.